Hello, I have decided to work with L systems for this project. So basically, this is how it works. We start off with our axiom, and our axiom is a start string of symbols that are defined in the constants and variables tab, and then each variable can be mapped to a replacement rule. So let's look at a simple L system. We're going to do starting off with the Sierpinski triangle. So we have our constants. Our constants are plus and minus, which is for rotating counterclockwise 2.0. Is that like 120 degrees, I think? I don't remember the exact number. Sorry. And then here we have F and G, which is move forward and draw a line. So each symbol is actually may or may not be mapped to a list of instructions, and each instruction has like a keyword, and some of them have parameters, some of them don't. Like draw a line doesn't have a parameter, but move forward 20 does. And here we have defined our replacement rules. You might notice there's no spaces needed. No spaces are needed because of the way I've created my parser. It's kind of different than a lot of other parsers in the sense that when we look for things, we just keep appending to our string until we find a keyword that's already been defined. And if we don't find one, we just keep going until we reach the end. So one of the key things about this that I'm going to show real quick is no substrings. So if we try to make another variable gg, that's just move forward 20, and then we're gonna actually have to define it. So let's just define gg equals that. But what it's going to tell us is we're going to get an error here, or a syntax or a semantics error, where it says that, hey, you can't do that because you cannot have substrings. And in order for the no spacing parser to work, we can't have substrings. So it's going to tell us like G is a substring of GG, and that's not allowed. So even if we do like giant dog, we're not going to give this just to show giant dog is equal to nothing, right? Oh, hey, look at that. We got some more substrings. So you're not allowed to have substrings. The easy way to fix this is to just use one letter name variables, and everything is maintained. So that's all on this parser syntax side. Yep, you can't declare it more than once. Yep. Okay. Here's we can animate. Once we've built our L system, we can now animate it, and here's a little animation. So you can see what's happening here is this is our replacement string up here at the top, and what we're showing is that as we're like iterating through it, how it's being decoded and what instructions are being called. So G, move forward, draw a line, and then plus is the rotation. Let's speed it up and you can see like exactly how it's working. This is taking a little while. It might be taking too long. Well, it should be done soon though. There we go. And very nice. Very nice. Okay. So that's the animation of the Sierpinski triangle being drawn. And we can actually rotate this by editing this variable right up here. So let's do 2, -1, and let's render it. So we're changing the starting position. We're going to save this as st.sierpinskitriangle.png. Hey, look at that. It's been slightly rotated. I don't know. Let's do 6, -5. What? Huh? Oh no, it's working. Oh. Whoops. Okay. So this is so you can see how it rotates. So you can change the starting direction to rotate your L systems. Another thing real quick. Let's do a demonstration of this right here. This is a tumbleweed. Let's do 3 generations, and then now let's animate this. So what this makes use of is the pushing and popping of directions and positions to the stack to be then loaded later. And when we animate this, you can see right here, this is where we're displaying that information. So let's speed this up. You can see that whenever we push the stack, it's being stored right here, and you can see like a visual representation of that. Now let's speed this up. And this is the L system that's being drawn. You basically get the idea, I assume. So let's save this now. Let's render it. This is the output. So now there's So that's pretty cool. So, but the problem with this is that every time we do it, we keep getting the same image because it's deterministic. So we can actually implement a little bit of non-determinism for randomization. And this is done by adding an extra parameter to the commands rotate counterclockwise, rotate clockwise, and move forward. So if we add this extra parameter, 50%, 50%, and 50% right here, we're telling it basically that whenever we move forward, we're going to randomize that amount by some percentage. And same with the rotate and clockwise. So and we're going to save this now, and we're going to see how our output changes. Oh, the problem there is that I didn't build it. When you edit the text here, you have to recompile. So let's save this again. You can see it's slightly changed. And if we do it again, hey, it's different this time. Let's actually increase the generation count to 5. Hey, wow. And again, just get one last look. Hey, we got a different one every time. So that's just a quick way to implement non-determinism. This feature is only available for the rotate counterclockwise, clockwise, and move forward. And we actually have a list here in this help section. It's going to give you a list of instructions in our instruction dictionary. What we have for that basically is it's just like a list and an explanation of how to do it. So that's basically all on that front. And you can only do it, Yep. Okay. Now then, let's actually show some other stuff that's pretty cool. Let's actually, this is something I should mention before anything else. So we can actually export this setting. This is different from rendering because what we're doing here is we're saving the rule set itself. So we're going to save this as tumbleweed, and we're saving it to our desktop now as tumbleweed.lsrs, and that stands for L system rule set. And then if we were to undo this, let's load in the curve rule set, and then let's import the tumbleweed.lsrs. You can see that the program state has been saved, and that's how you can share your L system with somebody else. So what I'm going to do now is I'm going to import. I'm going to go to 355 projects, finalized, fractal binary trees. This is an L system that I have created for fractal binary trees, and what we're doing here is we're making use of this command right here, scale line, increment thickness, and scale. And what scale does is it just every time you move forward, we're taking the move forward variable 1000 and multiplying it by 0.7017. So that's, I think that's just square root 2 over 2. And when we get the less than k1, we're unscaling it. So this is like the inverse of that. So we're undoing the scaling that we've already done, and you can see how we're doing that in our rules. So each generation in, our line gets smaller by a factor of square root 2 over 2. And then when we do the other side, so yeah, that's basically what's happening there. And let's build this, and let's render this to the desktop. Fractal binary tree.png. This is the output. One thing you might notice is that we're getting different colors. The color is changing over time, and that is a feature that I've added. Basically what this feature allows is, it's a rendering option, it's called depth-based colors. And what this will do is each generation in, we associate a color. So our colors, we have an initial color, which is black, and we have a destination color, which is green, and we're telling it basically each generation we're going to get more and more green until we reach the final generation 15, which should be completely green. And that's how you do that. So let's actually change the destination color to a light blue color, and then we can also change the background to I don't know, this color. And then let's save this again. And you can see we're getting varied images, varied colors, which is neato. And this is you can also change from radian to degrees, but that's self-explanatory. That's about all. But what if we were to, so you might ask yourself, what if we were to change these variables right here? Let's make this 45 and 90. So let's see how this modification has edited the image output. Hey, we got a different looking binary tree. And what if we did I don't know, 77 and 28? Hey, well, that's interesting. We're getting different ones. So you might actually want to imagine what it would look like if we were to take this angle right here and start to rotate it in real time in some direction, like that. And I've actually compiled these into an animation so that you can see what that actually looks like. So if we go right here, this is the starting image state. So this is our settings. We have the angles basically set to 45 and 90, and we're going to see what it looks like when we rotate one of them clockwise, or this one clockwise. So you can see now in real time what that is looking like, and that's looking pretty cool. So what about the other angle? What about the other angle? Well, this one now we're doing counterclockwise, and you can see how it's changing in real time, which is pretty neat. And we're varying, so this is a different start state. Add then, what is this set to? 30 and 60 degrees, and this is our rendered image. Kind of hypnotic. It's like you're looking at a hypnotist's watch, right? I might try not to get hypnotized myself here. I really like these. These are very nice. Pretty cool looking. Very, very nice. Okay, this video is getting long. Sorry. We have some more stuff to show. So I've actually gone to Wikipedia and I've looked at the Highway Dragon rule set, and I've improved it. I've modified it to make it better. Objectively better. So here is our Highway Dragon modification, and let's do basically this is just to look at it. I've actually made an animation of how I've improved it. So this is what this image would render and look like at generation 20. So I've made like an animation of it rendering. Okay, so this is the animation. This is basically just what's happening each generation. And you can see how it's continuing to get more and more detailed with each generation. What my L system does is different from the one on Wikipedia is because this is how it generates naturally. We don't have to edit or rotate these images in any way. This is naturally how it renders, which is pretty cool. And here's the same thing but without replacement. What's happening here is that we're just not replacing the old image, so you can see how it changes with time. Yeah, pretty neat. Okay. So let's go back up. This is a modification of the Highway Dragon for the golden ratio. We've just repurposed the old one and we've changed. So now we have 2 different angles for our triangle, and we have 2 different scaling factors for our lines instead of just square root 2 over it. So it's no longer an isosceles triangle. And I'm going to show you what that's going to look like real quick. Okay, so this is how it renders. You can see it's becoming more and more detailed until you get there. Wow. That's really something. This is just the full, this is image, and this is what it looks like without replacement. This is what it looks like without replacement. So you can see how like the patterns are forming. And how each point kind of lines up with the next one. So like this line right here is generation 1, and it starts in the same position and ends in the same position in each generation, which is very cool. Okay, so this is an L system I've created myself for Pythagorean trees. Well, let's just show real quick how this look. This is at, let's do generation 3, and let's do an animation of that. You can kind of see how this is gonna, like that. So that's basically the idea of what a Pythagorean tree is. So now if we go here, this is what it looks like at generation 15. pretty cool. So this is an animation of it rendering generationally. You can see how it's starting to change and curve inward. My mom said it looked like a shell, which I kind of agree, it does look like a shell. That's kind of cool. We have like the angles, actually they're set to, let's go back right here. So this is like, this angle right here is like 60 and this one's 30. And then each time like we do the same stuff. But what if you could ask yourself, like, what if we were to change these angles? So I've created an animation of how the tree varies when you change the angle, and that's this right here. And here's the same thing, but instead of using polygons, we're using lines and line segments. Kind of cool. So this is a modification of the Pythagorean tree. It's called a coniferous Pythagorean tree. And if you want, you could do like a little quiz yourself to see if you can figure out what's changed between this and the previous Pythagorean tree. So you could like see if you know what's going on. So right here, this is the key difference. Give you a little hint, maybe like what is going on. I'm actually gonna go. I'll show you right now. Okay, so this is how it generates. What you can see happening is, well, you look right here, basically what's happening is each generation we are swapping A and B. So this is, if this is angle A right here at 60 and this is angle B at 30 right here, well, A has now become 30 and B has now become 60, and we swap basically every other generation, and we get a varied tree. And we can also see how what that looks like when we modify the angles. This is the real-time animation of angle change, and that's my and here it is with lines. So this is another modification. This is a semi-coniferous Pythagorean tree. And if you can see basically the pattern here, we're using more baked-in memory, that is in the sake of variables, so that we can keep track of the state that we're in, and then we can achieve storing and swapping every other couple of angles. So let's see how that renders. So this is how the semi-coniferous Pythagorean tree generates. Pretty cool looking. So basically what's happening is, again, A, B, A, B. Now it's B, A, B, A, A, B, A, B. So it just, the same thing, swap angles every other generation. And here is an animation of that when we vary angle A and B. And again, with lines. That's about all for the L systems.